we had to switch out the mic thing, so
We heard it out there.
it took a while. Yeah. I hurt my ears. All right, so the next topic is airway resistance. And we have a graph and this equation for you to understand. Let's talk about the equation first. Airflow, delta P, capital R resistance. So in our lecture, flow is now airflow. And the delta P, we talked about before break when I said you make a change in the lung volume. And you change the intrapulmonary pressure. It alternates between -1, 0, and +1. We talked about that. Resistance to airflow depends primarily on, well, it's always, like I said in the previous lecture, friction. Friction of air rubbing against the airways. So now let's begin to look at the figure there. In the anatomy lecture, we went through all the divisions of the airways after you divide the trachea into the primary bronchi, secondary, tertiary, and we went through all the orders of division all the way down to the alveolar spaces. And so what you should note is that as you divide, the airways become more numerous. 1 becomes 2, becomes 5, becomes 18, and then after that, it becomes too many to count. But the airways are getting smaller. So a smaller airway means increased resistance to airflow. That's the relationship. Decrease airway diameter increase capital R resistance to airflow. However, look at that big drop-off after the medium-sized bronchi, after around the 7th division or so. Remember that even though the airways are getting smaller, you're getting more and more of them. So smaller airways, yes, but because there's so many of them, the resistance to airflow drops dramatically. So that by the time you get to the respiratory zone, the anatomy is, well, there's no resistance to airflow due to the diameters being so small, because there's so many. So this is true. However, in our respiratory system, the anatomy is in the respiratory zone. The airways are so numerous that resistance is minimal. The airways are so numerous, capital R resistance is minimal. And you have like 80 million of these small bronchioles. I went through the numbers already, but that's the concept right there. So friction doesn't really play a role when you have so many airways. But there are other things we can consider, like bronchodilation versus bronchoconstriction. During normal quiet breathing, the parasympathetic nervous system is kicked in and you're more or less bronchoconstricted. If you have to increase airflow because of increased metabolic workout from your exercise, then the sympathetic nervous system will kick in, you'll dilate a little more. Pretty much, if you bronchoconstrict too much, maybe you're asthmatic, or you have a spasm of the smooth muscle, the bronchioles. So there are other things. I mean, like allergies can cause it. Irritants, dirty air. Okay. So there are, environmental factors that can affect the bronchoconstriction. Sorry, I left out an R there. And just always remember, bronchodilation That's a sympathetic response. And the reason why I'm noting that is because for blood vessels, it was reversed, wasn't it? Let's think back, blood pressure. You vasoconstrict the arteries to keep blood pressure up. But for this system, it's different. The smooth muscles are arranged in a way, the sympathetic response dilates the airways to increase airflow. Okay, so, reverse. All right, so I want to move on. So airway resistance is something we like to mention. The control of respiration is also a topic that we consider too. The neuronal controls for breathing are in the brainstem. The medullary pons centers control breathing rate to maintain O2, CO2 levels. And the one that is tightly regulated is for the blood gas CO2, not O2. Now, I define it quite simply: hypercapnia, too much CO2, hypocapnia, too little CO2. Let me go through the flow chart that shows you how it's controlled by the brainstem. So we're trying to regulate blood levels of CO2. Partial pressure, CO2. In arterial blood, it's around, to put a number to it, it's around 40. In arterial blood. What this shows you is if it rises, let's say it gets to 45. You have blood gas receptors that can pick it up. So, let me read through. You have central chemoreceptors in the medulla. You have peripheral chemoreceptors in the same locations where you have the baroreceptors, carotid aortic arch. Okay, so there are bodies there peripherally that can detect that 45. And so the afferent pulses go to the medulla, the brainstem, and the efferent pulses go to the respiratory muscles, and they show you a diaphragm. The end result is, just to kind of shortcut this, it goes to the medulla, which goes to the diaphragm and other muscles. And you would increase the ventilation rate to regulate arterial levels. Increase ventilation. That means breathing. Respiratory rate is typically something like 12 to 15 breaths a minute, something like that. Increase respiratory rate. Okay, that's usually measured in breaths per minute. All right, so then that would help re-regulate the PCO2 back down to around 40. So you don't have to change it much to trigger a response, because CO2 as a blood gas is tightly regulated because it can mess up the pH. By hypercapnia is too much CO2, it can decrease the pH. I think I showed this to you before, just as a reminder. It can generate carbonic acid, which is a weak acid, which can partially dissociate using a proton. Okay, so it can alter the pH. So hypercapnia is an elevated level of CO2. In the brain, there's no proteins in the brain to buffer the added hydrogen ions. So that's why this is a danger. And so that's why you induce the ventilation. What I say on the slide is if the PCO2 reaches 45, it will double the ventilation rate. Now the opposite is true. Hypocapnia causes problems. So hypercapnia, a problem. Hypocapnia is a drop in the partial pressure of CO2. What you may not know is that CO2 is a vasoconstrictor in the brain. I'm sorry, I said that wrong. CO2 is a vasodilator in the brain. So when the level drops, you get vasoconstriction. That makes you pass out. Of course, when you pass out, you stop breathing, but that is actually advantageous because you allow CO2 to accumulate. So if you see someone becoming faint, don't let them pass out. Catch them, sit them down, let them rebreathe their own air in a paper bag or something, right? You've always heard that. This is what you're allowing the CO2 to accumulate because you get panic, you hyperventilate, you breathe off too much CO2, and you cause yourself to become faint and pass out. So CO2 is tightly regulated. Not so much O2. O2 has the hemoglobin. Hemoglobin is a huge reservoir. So much so that you need to see a big drop in PO2 before you see an increase in ventilation. So that one is not tightly regulated because most of your O2 is circulating. It's still bound to hemoglobin. Even when we say hemoglobin, like blood is oxygen poor, we've been saying that all term. Really, that oxygen poor blood is still 75% saturated with oxygen. Okay, so it's really still circulating bound to hemoglobin. Normal PO2 is around 100. You need to drop in to about 60 before you notice a change in ventilation. Okay. Other concepts. The idea of anatomic dead space, which is kind of a misnomer. There's nothing dead. It's just referring to the conducting airways where there's no gas exchange available. That's the dead space. We'll put it another way. Dead space volume. I've been drawing this respiratory system as this little flask. And let's pretend you have all this fresh air that you're breathing. Let's say this is the air you're going to suck into your lungs. So you suck it in. And take a nice deep breath, and some of that fresh air occupies this space. Some occupies this space. This is the desirable space. The alveolar space is where gas exchange can occur. So this space is like the dead space volume because no gas exchange is occurring. Nothing's dead, it's just the conducting airways. Air sitting in the conducting airways. Your trachea, your large bronchi, your bronchioles. We talked about that. Well, anyways, let's say of that 500 ml fresh air, let's say 150 is like the dead space volume. Only 350 reaches the fresh air. And it's more detailed than that, but just as a rough estimate. The point I'm trying to make is not all fresh air reaches the alveolar space. You can measure how much you're breathing through your mouth. We're going to do that in lab. But not all of that space is occupied by all the air you breathe in. So if the normal tidal volume, VT, air you breathe in is 500, which is a typical number, maybe 350 reaches the alveolar space and is available for gas exchange. So if you want to subtract out the dead space volume, we call that the alveolar ventilation rate, not just ventilation rate. For alveolar ventilation rate, subtract out dead space volume. The 150 is a nice textbook number. That's usually the volume of air that will sit in the large bronchi, the trachea. Yeah, so that 150, it's not available for gas exchange. Okay, so we call that the dead space volume. Or you could have like some lung problems. A non-functional alveolus where no gas exchange is occurring can be considered alveolar dead space. So, you know, well, what you could do is think about it this way. I guess dead space becomes real in suffocation. If we reduce the ventilation below that of dead space volume, well, there's no alveolar ventilation at all. So say, for example, you have a large snorkeling tube that has a volume of 350, and your actual anatomy is another 150. So that means if you're only breathing in 500, theoretically, there is alveolar ventilation, even though, let's see, if tidal volume is 500, theoretically there's alveolar ventilation, even though ventilation rates are normal. Consequently, a swimmer could suffocate. So basically, look at it this way. So pretend that that's the snorkel that adds an additional 350 on top of your 150 that was already your anatomical dead space. The snorkel is not part of your anatomy, right? So, but you're trying to snorkel, so it's like you're not breathing. You have to take a much deeper breath. That is all filled with 500. If you only breathe 500, what I'm trying to say is there's no fresh air reaching the alveolar spaces. It's all stale air, okay? So you would suffocate. That's the point I'm trying to make. So that's why you can't breathe through a garden hose at the bottom of a swimming pool. How much of that is fresh air? 0. You might get 1 breath of fresh air, the air that's in the garden hose. But as soon as you suck that one time, it's gone. Okay, and you're going to suffocate. So that's why that doesn't work. All right, so let's see here. Okay, so to kind of work the math out, you have dead space volume, 150, but you can vary your tidal volume. You can take a normal quiet breath, you can take a deep breath, and you're breathing at a certain rate. Average is something like 12 to 15. Okay, it's one of the vital signs of life. You might want to like monitor your patient's respiratory rate. Just look for their chest to rise and drop. It's not hard to do. Okay, and then you can kind of calculate out. This symbol is for alveolar ventilation rate. D sub A with a little dot above it symbolizes alveolar ventilation rate. And so kind of here's the math. All right, so to get this number, let's do the first one. You're just sitting down, and well, what I would first do to calculate alveolar ventilation rate, subtract dead space from tidal volume. So that way you know how much air is actually reaching the alveolar spaces. That's step 1. So I'll go. Oops, I'm sorry. Thinking ahead. That's how much is reaching the alveolar spaces per breath. Did I lose anyone there? I just subtracted tidal volume. I'll call it TV. versus dead space volume. Tidal volume, like the tide going in and out every day. You know, it's just like normal quiet breathing. You don't think about it. You just breathe in and out every day. A normal quiet breath, something like 500 ml. Now, when we do it in lab, we usually measure. It's difficult to breathe. Like we have this setup where you gotta wear a nose clip, and you're breathing through something, and people are watching you, and you got this big mouthpiece. Like, so you might measure something different, because it's hard to breathe normally with all that equipment hanging off of you. But normally it's about 500 ml. Okay. And so, boom, we got our 350. That's how much is reaching the alveolar spaces per breath. But what's the respiratory rate? Let's say it's 15 breaths per minute. So now you get the units to cancel out, breaths. And, well, 350 times 15 should give us that number. Okay, I need a calculator. Yeah, 5250. Mils per unit time, minute. So what's liters? 5.25. Okay, so you're expected to, if the units change, and you know it's equivalent. And so I'm not going to do the rest, but you can see the difference. It's better to take slow, deep breaths, like while meditating or just relaxing in a quiet room. And it's hard to get a quiet moment. But it really does help. At least from a physiological standpoint, you're increasing the ventilation rate. Now, a problem I might have you solve, question for you. Let's say I do the first one. And I'm wondering if you could do the second one by yourself, like on the test or something. Let me do the first one so you can map it out. Someone jogging on the beach. Sarah's normal alveolar ventilation rate during mild exercise is 6 liters a minute. So that's how much she needs to ventilate her lungs so her muscles can get enough oxygen. 6 liters a minute. While at the beach on a warm day, she goes for a jog. And I'm asking, well, what would her respiratory rate have to be for her to maintain that AVR of 6.0 liters per minute while jogging? And you can assume the usual 500 ml tidal volume and about 150 dead space volume. Okay, so let's set it up. So I'm just going to subtract out the dead space volume right off the bat. I keep doing it. So per breath, 350 ml of fresh air is reaching the alveolar spaces. So what we're trying to figure out is multiply that by unknown X number of breaths per minute. We know that that will equal her given 6 liters per minute. Now the units are different, so I've got to make them the same. I'm going to convert 350 ml to 6 to liters. So I'm going to go 0.350 liters per breath times X breaths. That's the unknown per minute equals 6. And don't get lost in the numbers, just think conceptually. How many breaths per minute does Sarah need to take to get your 6? Okay, so what are we solving for? X. We're solving for this right there, right? X number of breaths. So, I'm just going to do the simple algebra there. I'm just going to divide both sides by this figure here. X number of breaths per minute equals 6.0 liters per minute times, I'm just going to flip that. Yeah, that's right. Those liters cancel out. Okay, so 6 divided by 0.35, should be like 18 or something. Yeah, 17.14. Well, I don't know what 0.14 breath is, but I just did the math. It's about 17 breaths a minute. Okay, that makes sense, right? With the dead space volume, you have to, I'm sorry, oh gosh. You know what I did? I did this one for you. Oh, shoot. Okay, that's okay. Are they the same? Oh, wait, no, I didn't do this one. I did it right. Okay, sometimes I get up here, I start panicking. I did it right. So let's review. Boom, boom. What is the 150? Okay, I did do it right. I was thinking that was the historical, but it's not. So I did it right. And we said that, did I lose anyone in the math? I'm not a math teacher, but I know what I'm doing. That was pretty basic algebra. Did I lose anyone on the math? Maybe you need to do it again yourself.
Yeah.
Okay, but let's just conceptually now talk about this. We calculated correctly. Jogging on the beach, she needs 17 breaths a minute. Now the second problem, everything is the same, except now she's snorkeling, and the only added thing I'm throwing in there is this, 50 ml additional dead space volume. Okay, so everything's the same, except now we're adding more dead space. So just think conceptually. If you have more dead space, and you want to achieve the same ventilation rate, are you going to have to breathe more or less? With more dead space. You're going to have to breathe more, because you're going to be ventilating less. So that's what you should calculate. And to do the calculation, what are you going to do differently? This number is going to change to what? 200. So instead of this being 350, it's going to be 300. And you just do the math and see what you get. So that's kind of how I set these two problems up for you as a question for you. So in terms of being able to calculate math, we also need to talk about other volumes besides tidal volume. The idea of spirometry, and this goes right into the next batch of slides called spirometry for those of you that print out slides. I'm going through right now because this lab we're going to do on Wednesday. So I want to be sure I cover it today so you know what you're doing in lab on Wednesday. Spirometry is measuring changes of the lung volume. The max volume of all airways in an adult is something like 5 to 6 liters, maybe a little bit less. It depends on your stature. Respiratory physiologists have defined a series of volumes and capacities that are easy to measure with simple lab equipment. We're going to do it. These values may provide useful insight for clinical assessments. And what we're asking here is, how well can your subject move air in and out of their lungs? Okay, you should be able to measure how much. So what we're going to do, I'll demo it on Wednesday. We have to calibrate our equipment, and then you have a real person do it. The calibration, we have these syringes that act as, they're air pumps, and they simulate breathing. And then so if you can kind of calibrate your airflow transducer, then when a real person breathes, you can accurately measure. Okay. Now, this setup, I usually don't talk about technical specifications with students, but over the years, students have really messed up our syringes. The big mistake is, look how this is properly done. So look at both hands. One hand is on the plunger, and the other hand is on the body of the cylinder of the syringe. It's not on here. A lot of students like to put a hand here and then you start pumping, and all of this breaks down. You start breaking the seals, and then you get inaccurate calibrations, and your numbers are all wrong. Okay? You're trying to tell the machine this is an approximate breath, but if it's wrong, then it's going to mess it up for your subject. So that's one thing. And look at what we do. We put a sterile filter, one-time use, in between you and this permanent piece of equipment. What you can't see is this has a metal diaphragm that has electronic wires that go to the computer. The metal diaphragm is mesh, and air is allowed to pass through it. That is how we're monitoring the airflow, so we can measure the volume of air. However, if you're constantly putting people's breath across it, you need to keep it sterile by putting that filter there. Now, do you think in the history of this lab, someone has forgotten to do that? Yes. Even my students have, even though I'm very adamant about it. So there are germs on there. And so you want to protect yourself by having that filter. Maybe you don't care about our equipment, but maybe you care about yourself. Put that filter on there. You do it both for the calibration and, of course, when your subject is on it. So that might be the most important instruction. Protect yourself. All right, so the other thing is, what's the readout going to look like? Something like that top picture there. Just breathe in and out, in and out. So the spirograph you should generate, you should take, I would say something like 5 normal breaths through subject. You're just sitting there, normal quiet breathing. Okay, 5 normal breaths. Breathe in, breathe out. Maybe that's one breath, one little hill. Take 5. In and out, in and out, in and out, in and out. Then take a super deep breath in, and then try to blow all out as fast as you can. And then in and out, maybe another 5 times. That's it, that's your data. But you want to have one super deep breath all the way in, all the way out. That's very important. So that'll measure your capacity. If you're a larger person, maybe you're athletic, and you expect to have a bigger breath. Okay, and people who have smaller body frames will have a smaller breath. Okay, but the important thing is to give a max effort, so it's not shrunk more than it's supposed to be, because you don't know. You're just going to measure it. But as long as your subject gave you a max effort, it should match with what we expect to see. So the things that you can measure, a normal breath, this first one, tidal volume. Let's say it's just from there to there. Call number 1. Tidal volume. And it describes the amount of air inhaled and exhaled with each breath under resting conditions. Normal quiet breathing is what we call it. Okay, well, inspiratory reserve volume. And they give you the textbook average for males and females. And males on average are larger in stature, so the numbers are a little bit higher. Okay, so on average. All right, so IRV. Number 2, IRV. The inspiratory reserve volume. I won't write it out. It's right there for you. Just call it IRV. But basically, if you're a measure in the lab, you have to measure the top of this point to the top of that point and take the difference. That's the IRV. Okay. Makes sense. Inspire, the reserve. You can take a normal breath in, but you can breathe in more. Right? So it's that deep breath. The difference between, what is the reserve? The reserve for a breath in. And then you have the expiratory reserve volume, the ERV. So look at the end of a normal breath out, but then look at the gasp of you pushing it all out. There's some reserve there. This ERV is usually much less than the IRV. You can like take a deeper breath in, then you can push more out. Okay? Because the lung wall is stuck to the chest wall, right? It's easier to inflate a little more than push out a little more. So we can look at the numbers. It's about a liter, all right? About 1,200 in a male, 700 in a female. Then there's this volume of air you just cannot get out of the lungs no matter how much you try. Let's say this is the graph. Put axes on it. You have this distance from there to there. They call that the RV, the residual volume. When you reside somewhere, you're not leaving. You live there. This is the volume of air in the lungs that you cannot get out. Why? Because the lung wall is stuck to the chest wall. If you were to completely deflate both lungs, well, yeah, then you could push it out, but then that's a collapsed lung. We don't want that. Okay. So that's the volume of air you can't get out. It's about a liter. They say about 1,200 and 1,100. Well, anyways, these volumes can be added up to different capacities. For example, if you added up the total lung capacity, I'll just go in order that they're going for. So it's like all of it, from top all the way to the bottom. That's your total lung capacity. I mean, what could you add to add it up? You could add up the IRV, the TV, the ERV, the RV. They all add up, right? Now, that one we cannot directly measure in the lab. We cannot directly measure the RV. We have to assume what it is. Again, the only way you can, there's ways to measure it, but we can't do it. So, what we can measure is the vital capacity. Vital capacity. So that's the difference between here and there. Deep breath in. You can directly measure that in the lab. You're going to see it on the graph. You can measure that one. I would say that's the most important one to look at. If I'm doing it for myself, that's the one I want to see. I want to see what my lung capacity is in terms of VC. Almost 5 liters for a man, maybe 3 liters for a woman. Okay, inspiratory capacity and FRC. That's it. Like from the end of a normal breath, breathe in all the way. That's how much you can inspire, all of it. It's your TV plus your IRV, okay? Well, it's easy to see when you graph it out like that. And then the other one is functional residual capacity. So from like here, column number 4. Well, I'll just put it right here. I don't have any room there. The functional residual capacity. Earlier today, I said that was the moment before you take your next breath, right? That's where it would be when you're breathing a spirogram. You breathe in, you breathe out, normally. Before you take your next breath, understand there's a lot of air in your lungs. There's all of your ERV and your RV. It's all there. So the FRC has a very important function. The F is for function, right? It's like a mixing chamber, so that as long as you're breathing fresh air, blood is always going to exchange with your alveolar spaces. And it doesn't matter if you're breathing in or out. If you breathe out, you can still get oxygen into your bloodstream, even though no fresh air is coming in, because you're actually breathing out. It's because of this big mixing chamber of FRC. It's a nice O2-rich mixture no matter what. The only thing that would mess it up is if you hold your breath. Okay? But as long as fresh air is coming in, FRC will always allow oxygen to enter the bloodstream and CO2 to leave the bloodstream. Well, anyways, we'll measure those things and to talk about some pathologies that cause gas to not be exchanged well. There are two categories: restrictive and obstructive lung disease. Restrictive, obstructive. Okay, so let's read my bullet points here. Restrictive is actually very descriptive of what it is. It talks about the ability of a lung to stretch is compliance. I mentioned that. A compliant lung is pretty much a good thing. A high compliant lung stretches easily. A low compliant lung is a stiff lung. It requires much more force from inspiratory muscles to stretch it. Diseases that decrease lung compliance are called the restrictive lung diseases. Ventilation is affected because more work must be expended to stretch a stiff lung. So basically, restrictive lung disease means it's difficult to inflate a stiff lung. Okay, let's read through my notes for obstructive lung disease. Normal breathing sounds resemble a whoosh if you're listening through a stethoscope. Diseases in which airflow is diminished because of increased airway resistance are the obstructive lung diseases. When patients forcefully exhale, air whistles through narrowed airways, causing a wheezing sound that can't be heard even without a stethoscope. So maybe it's easier to inflate lungs easier to breathe in, but it's difficult to empty because of the obstruction. So generally, those are the conditions, and there are some causes that fall into either one of these two categories. I'll go over some of the commoner ones. Emphysema is considered an obstructive lung disease. It's a destruction of alveolar walls. It produces a smaller number of larger alveoli, and that's not really a good thing. Larger is not better here. Because the alveolar spaces will have less surface area. Maybe the lungs are overly compliant due to the destruction of the elastic fibers, maybe due to, say, cigarette smoke, the toxins destroy elastic fibers. So it's easy to inflate but difficult to empty. So again, instead of having, say, 1, 2, 3, 4, 5, 6 nice little alveolar spaces, maybe have one big one. Less surface for gas exchange, so less O2 exchange, so the oxygen tension leaving the pulmonary circulation. It should be oxygen rich, but it's not. It's very low. So gas exchange is impaired due to the increase decreased surface area for gas exchange, but also more sterile air is being left inside the lung because the lungs are difficult to empty. So as you're breathing in, you're just not ventilating as well. Okay, that's a poor rendition of emphysema lung, but you get the concept is it's obstructive. Technically, there's no obstruction in the airway, but we categorize it here because the lungs are difficult to empty because of the lack of elastic tissue. Here's a picture of emphysema lung. I don't think you have to be a doctor to figure out that if that's normal, that doesn't look good. Looks like a big mess to me. Look at under higher magnification. Emphysema produces a smaller number of larger alveoli. I mean, I don't even know how you exchange anything with that. There's no structural integrity compared to the normal lung. So know what emphysema lung looks like. There are other fibrotic, the next one is fibrotic lung disease. This is the classic restrictive lung disease. Like cystic fibrosis, as an example. Fibrosis is characterized by the development of scar tissue that restricts inflation of the lung. The thickened respiratory membrane slows gas exchange. The loss of lung compliance also may decrease alveolar ventilation. So how they illustrate that is, the picture on the right, see the thickening of the respiratory membrane? That will impair gas exchange. But also, you're not ventilating as well. It's difficult to breathe. A pulmonary edema. An edema is a swelling, fluid accumulation in the lungs. So you're putting a gap between that respiratory membrane. When you increase the diffusion distance, you decrease the oxygen tension of the pulmonary blood. So that's considered restrictive as well. Let's say the left heart, you've had a heart attack, you can't push the blood forward, so blood backs up into the lungs, and well, anyways, that increased. The reason why this is restrictive, I mean, it's like trying to blow a balloon up underwater. It's difficult to do. So that increased fluid around the alveolar spaces restricts the inflation of the lung. Okay. This is the classic obstructive lung disease, just asthma. Maybe due to allergens, breathing dirty air over time, bronchioles constrict, and it's difficult to ventilate the lungs with the increased resistance to airflow. So oxygen tension will be low. Well, those are some common diseases, restrictive, obstructive, and the test that we can do in the lab, well, what you could do is just measure the minute ventilation by just kind of like measuring tidal volume and multiplying by number of breaths. There's also a test we'll do, it's called FEV1, and this is forced expiratory volume 1. The 1 is how much air can you push out in 1 second? How much air can you exhale in 1 second? So that's the test that you'll do Wednesday. And so let's talk about it since you're doing it on Wednesday. Think about Wednesday. I'm going to group you. I got to shrink you from 10 groups to 8 groups, so to make it less of a hassle, I'll put you in groups. And but for each group, you got to choose 2 subjects. I think it's good if you do one and then do another, just so you can kind of like compare 2 people. What I do is, if you read the lab, I say 1 normal, one COPD. Now, I don't think anyone has COPD, but just kind of like if you want to volunteer information about yourself, you know, I used to live in LA, I used to breathe bad air, I used to smoke. Man, you know, I would be good for the COPD, but of course it's all voluntary. But it's at least good if you just get 2 people, just compare. Okay. FEV1, you inhale all the way, and then all the mouthpiece, blow it all out. You should be able to push out 80% of total. Okay. You should be able to push out 80% of your vital capacity in 1 second if there's no obstruction. So here's what that might look like. You just breathe in off the mouthpiece and you put on the mouthpiece and blow all the way out. And notice it's very steep at first because you're pushing most of the air out. And then what students usually don't do is you forget the gasp part. You're supposed to gasp. You want to push every molecule of air out of your lungs that you physically can. So you get this nice little, don't stop there, just keep going and going and going. Try to gasp all the air out for a good 5, 6, 7 seconds. I mean, we're not going to measure FEV3. We're only measuring FE31, but we've got to get this max value. So you got to gasp for 6 seconds. I'll remind you, okay? Because usually students don't get good data here because you don't do the breathing out for 6 seconds. Every little last molecule of air needs to be pushed out. Well, anyways, I'll demo that tomorrow. Let's kind of look at the other thing I talked about, where you take normal breaths and a deep breath. I got this from another textbook. Okay, for obstructive lung disease, I would say the main thing to look for is decreased vital capacity, decreased FEV1 for obstructive. That's what we hear. And I would say the main thing to look for inflating a stiff lung, decreased VC. Actually, I would think VC might be normal if you do it right. So I'm going to erase that one from this side. A lot of times, if students are asthmatic, they won't push all the air out. They'll just kind of stop short. But if you should be able to. So I'm going to erase it from this column. It's more for this column. If you have a stiff lung, everything is squashed in the spirograph. You just can't inflate all the way. So that's what squashes the VC. For this one, you can breathe all the way in, but notice the steepness of that. It's less steep. It's difficult to push the air out. That's really what you want to look for, although the value might be normal. Really, the FEV1 is affected the most. So when you measure FEV, I put a line over 1 second. Okay. Now, the vital capacity for a normal person is this top value. And look at for obstruction. For the first second, you can barely push anything out. You're supposed to be able to push 80% out, but you don't. But if you just keep on wheezing the air out, eventually your VC will be normal. Okay? But that's not the case for restrictive. For restrictive, you just can't inflate the lung, so your max value is very low. And you're able to push it all out in 1 second. So you don't observe an obstruction. Just the VC value, the vital capacity value is very low. So I'll demo the lab tomorrow after I put you in groups. And I don't know if you noticed, but I put on Canvas a quiz. Okay? And I want to go through those slides to prepare you for the cardiorespiratory quiz, because that's due tomorrow.